Response chemical improvement so pre and post chemical so the other side wants patients to respond to they have more
We'll start now, 8:15. Good morning. Today's topic is muscle anatomy and physiology. So we'll be getting into the structure of the muscle, little bit in detail, and how it functions. So first we have the general structure. So as you see, so muscles go they go from insertion to it starts from origin to insertion. Now they are composed of multiple muscle cells, or otherwise called myofibers. Now this is a myofiber. What we're looking at here, the whole structure, which is cylindrical and long, is a myofiber. So these myofibers are extremely rich in sarcoplasmic reticulum and mitochondria. So, and they contain a lot of glycogen to produce energy for muscular action. Now, the important things that we need to look here are, one, what are they composed of? Apart from sarcoplasmic reticulum, apart from mitochondria, they contain something called myofibrils, which is very important. Now, these myofibrils, we would have learned in our physiology that they are composed of thin and thick filaments. So basically, for muscle contraction, we need overlapping of something called thin and thick filaments. So these thick filaments are nothing but myosin. So there are many contractile proteins, and these contractile proteins are composed in the form of a myofibril. So each myofibril, they contain actin, and they contain myosin, they can contain troponin and tropomyosin. So, and there are two bands. One is an A band and an I band. Okay. So this you see is the myosin, which will form the A band, and the thin one. So the thick and thin filaments, the thick filament is this one, which is almost double the size of the thin filament. And the gray lines are the thin filaments. Now, the thick filaments are composed of myosin, and the thin filaments are made up of actin, tropomyosin, and troponin. So when they overlap with each other, with utilization of energy, there is contraction happening. So there are cross linkages that happen between them. And these mitochondria and rich endoplasmic reticulum help generate that energy for the contractions to happen. And they're multinucleated. Each myofibril will have numerous nuclei. And they're covered by something called sarcolemma, and the cytoplasm is called the sarcoplasm. So we have the sarcolemma, we have the sarcoplasm, we have mitochondria, we have endoplasmic reticulum, and the most important part, the myofibril, which contains our contractile proteins. So now let's get into, there are different types of muscles, but we will be primarily talking about the physiology of a skeletal muscle and a little bit about smooth muscle. So to get into the difference, one, skeletal muscle location, they are somatic. They are located in the somatic musculature. Cardiac muscle present only in the heart. Smooth muscle, we know hollow viscera. Not only the hollow viscera like the gut, but also the uterus, the iris, they're all made up of smooth muscle. Structure, they have striations. and hence they are called striated muscle. Here, they also have cross striations, but they are syncytial in character. That is, there are gap junctions in between two cells, and an action potential generated in one is transmitted along, and they all work as a syncytium. That is one uniform unit, one unit. So there are two syncytiums in cardiac muscle. That will be atria acts as one group, that is one syncytium, and the ventricles act as one group, that is another syncytium. These smooth muscles, they are soft tissues. I mean, they don't have cross striations, hence they are termed as plain muscle. And they are again of two types. One is a single unit, which is again syncytial. That is, if you stimulate one, the depolarization is transmitted along loosely present gap junctions in between the cells. So the whole part acts as one single unit. Hence, they are called single unit. Whereas multi-unit, and these single unit, they have pacemaker cells like our muscle, like our cardiac muscle. So they don't need what do you say, an innervation and nerve innervation for it to function. It can generate on its own and a muscle contraction can happen. And there is always a baseline tone that is maintained. Whereas multi-unit, they are your sweat glands, the piloerection, the iris, they all have strong, they all are single units. In fact, every unit has an individual nerve innervation. Hence they are termed, and they need that nerve innervation to give it signal for it to function. So hence they are called multi-unit. And skeletal muscle are voluntary, smooth muscle involuntary, and cardiac muscles are involuntary. So let's get into the light microscopic appearance. This is what we studied in our first year MBBS in physiology. So to talk about skeletal muscle, like I told you, they are striated muscles because under a microscope, they appear striated. What do you mean by striated? So basically, there are multiple components which have different refractive indices. So basically how they refract light, they appear different and they appear striated. So A band is a dark band which appear, and it is anisotropic. It does not reflect. So A band is the A band. So there are two bands. One is the A band and one is the I band, and they contain multiple lines and multiple bands in the center of it. Okay, so the A band is the thick filament, I band is the thin filament. A stands for anisotropic, I stands for isotropic. These are the two important bands that we need to remember. And they are, so A band is anisotropic, so they appear dark, whereas I band is isotropic, they appear light. And A band consists of your thick filaments, whereas your I band consists of your thin filaments. In simple terms, we'll be talking about it with respect to a diagram. And now in the center of A band, we have something called H band, stands after the person who discovered it, which is Henson. It is a small portion which is fairly less refractile compared to the rest of the A band. So hence they are termed H band. Right in the center of the H band, we have something called the M line, which appears more pronounced. It's right in the center, and it is more pronounced during muscle contraction. And the small zone around the H zone, around the M line, is called the pseudo H zone. So these Z lines, they are important. We'll be talking about it now. Okay. So this is single myofibrin. This we are looking at it from top. So this will be your A band, which corresponds to this. Think we are looking at it from here, from the top. And this is how it appears. So this is the A band. This is the I band, the light one. So less refractile, more refractile. So the dark bands and the light bands. Now you see right in the center of the A band, we have something called the H band. So from this line to this line is the H band. So it appears a little bit lighter than the rest of the A band, hence H band. And now right in the center, we have an M line. And on either side of the M line, we have a little bit more lighter zone, which is called the pseudo H band. So, and this is the I. And right in the center of the I band, we have something called the Z line. So what is a sarcomere? Sarcomere is a functional unit, functional contractile unit. So basically from one Z line to another Z line is your basic contractile unit called the sarcomere. Now, apart from that, what we need to know is, So this junction between the A and I band is called AI junction. This is important with respect to transmission of depolarization, which we'll be talking about now. So the contractile unit of the muscle is a substance included between two adjacent Z lines called a sarcomere, and the normal length at rest is 2.5 micrometer. Now at rest, I band interdigitates with A band only outside the H band. Now we'll be talking about this. So you see, this is the this will consist of your A band, and this will consist of your I band. And you see, this approximately this will be your H. Okay, so at rest, we see the thin filament, that is the I band, reaches up to the head zone. But when it contracts, the A band, that is the A band, pretty much remains stable. It does not move. The only thing that moves is your I band, which comes closer and it overlaps and crosses the H band. That's why H band is a important landmark to remember. So during muscle contraction, the length of the A band remains constant, whereas Z lines move closer together, causing the sarcomere length to reduce to 1.5 micrometer. By stretching the muscle, that is now at rest, it is 2.5 micrometer, and the I band is present just at the junction of the H band in the A band. During muscle contraction, they cross the H band, and the size of the sarcomere will end up being 1.5 micron. But when you stretch it, when you stretch it to the point where I and A band overlap ceases, the sarcomere length becomes 3.5. So this is the maximum length to which you can stretch the muscle. So at that point, there is no overlap. Now, coming to look at this in a little bit detail, electron microscopic appearance. So electron microscopic appearance, we'll be looking at just the bands, just the contractile components of these bands. Now, in the thick filament, otherwise called your A band, you have your myosin. Now, this is twice the diameter of the thin filament, and it is made up of myosin. It is 10 to 11 nanometer thick and 45 nanometer apart, extending between A bands. So when this myosin component is broken by a proteolytic enzyme, you find that they're arranged in such a way that there are two myosin components comprising the A band. Now, each myosin component, they have two large polypeptide heavy chains and 4 light chains. They have 2 heavy chains, 4 light chains. Now, the reason why there is a H band in between is when you dissolve this with a proteolytic enzyme, the heads of the myosin appear as the lighter H band, whereas the rest of the body of the myosin appears as the less refractile dark A band. So these polypeptides combine to form a molecule that consists of 2 globular heads and a long tail formed by the 2 heavy chains. So your heads will contain both. In the head, you'll have 2 heavy chains and 4 light chains, whereas in the tail, you will have only the heavy chain. So this function of myosin, what does it do? There are 2 parts to myosin. When you dissolve it, you find out that the head contains 2 things. One is an ATPase enzyme, and the second is an active binding site. Now, what is the use of myosin? It has to bind to actin, that is the thin filament, and second, it has to generate energy. Somehow it has to break ATP, get that energy to do contraction. So that is done by myosin. So there are two parts to myosin, which is important. Now, that is about myosin. Let's come to the thin filament. Now, thin filament is made up of 3 things. One is your actin, troponin, and tropomyosin. Now, actin is, again, you have two types of actin. They are the thin lines, and they are multiple. So compared to tropomyosin and troponin, actin is multiple. For example, there are 300 to 400 actin molecules and only 40 to 60 tropomyosin molecules per fiber. So now they are thinner, 4 to 5 nanometer in diameter, stretch from Z lines to edge of head zone. Like we already discussed, there are 2 types. One is your globular actin, the other one is a fibrous actin. So the polymerized form of G actin, that is a globular actin, is your F actin. So globular actin has ATP attached to it, but when you remove that ATP to generate energy, so that's the function of myosin. So once the actin attaches that, the ATPase in the myosin breaks the energy, breaks the ATP present in actin and release energy for contraction to happen. Now, tropomyosin is nothing. They are found in grooves between actin. Their whole function is to avoid the contact between actin and myosin. Now, troponin is good. There are many types of troponin. One is troponin T, troponin I, and troponin C. Now, troponin I function I inhibition. It inhibits the interaction between myosin and actin. C. So the main function, so the main element here, which is responsible for contraction, is calcium. Why is this calcium initiates the whole contraction process. This troponin C, there is a calcium binding site attached to it. So when there is depolarization, there is release of calcium into the sarcoplasm. From the ECF into the ICF, the concentration of calcium in the ICF increases. Now this binds to the troponin C and it exposes. What it does is it binds to the calcium and it moves. Once it moves, the tropomyosin, which is attached to the troponin, also moves. So the myosin binding part of the actin is exposed. So troponin T binds other troponin components to tropomyosin. So because, I mean, if there is binding, then they all work as a unit, tropomyosin and troponin. So troponin I keeps the tropomyosin in place and blocks the attachment site between actin and myosin. So the troponin C, it attaches, takes in calcium, moves the tropomyosin away. So they all works as a unit so that the active part, the contact part can be exposed so that it can connect. Now, we'll be talking about something called a T-tubular system, sarcotubular system. So this is how a depolarization present extends from the sarcoplasm, which is the surrounding layer, into the myofibrils. So since there are so many myofibrils, there runs a system parallel to each myofibril called the sarcotubular system. Now, sarcotubular, as the name says, you have the reticulum, sarcoplasmic reticulum, and the tubule formation. So what is a tubule? This is a tubule. And this is a sarcoplasm. This whole structure is called a triad. So what happens is when the depolarization is set, so the calcium from here, these are voltage gated dihydropyridine channels, and these are not voltage gated ryanodine calcium channels. So this is present, this is the inside of the cell. This is the ECF. Now the membrane, this is the sarcolemma. This sarcolemma sends out projections inside and connects with the endoplasmic reticulum, which I told you is very important from energy generation. And there are lots of it in a skeletal muscle. So these are the long end of the sarcoplasmic reticulum, longitudinal filament. So they contain a lot of glycogen and a lot of calcium. It is all stored here. Now this end of the longitudinal sarcoplasmic reticulum is called the cistern. And this cistern contains a lot of calcium and it is stored. Glycogen and calcium is stored there. But the only way we can cause depolarization of the cells and the rest of the myofibril is to release the calcium from it. How do we do that? Once the depolarization reaches the membrane, this is a sarcolemma, it goes along the T-tubule system. T-tubule system is the way of transmitting the depolarization into the cell. So these voltage gated channels get activated and there is calcium release. Once there is calcium release from here, the ryanodine channels also gets activated and there is calcium release for here. So during this, not only do you have calcium coming from the ECF, but also the stored calcium from the sarcoplasmic reticulum also comes. So it is said that approximately the calcium concentration increases up to 2000 times its level to cause contraction. So this is a very important functional unit. And this is present. Why I told you AI junction is important is because there are only 2 AI junctions per myofibril, and that this can be present only in the AI junction. So there are only 2 triads per myofibril. So this is another way. So you see, this is the T tubule I was telling about. This structure is a T tubule. This is a terminal cistern, and this is the sarcoplasmic reticulum. So this is a terminal cistern. This is the ryanodine receptor, which is not voltage gated. It's just open. It will come out. So calcium release flux, and so basically it creates a current. So this is voltage gated. Once the depolarization reaches here, calcium from the ECF goes out, enters the cell. And at the same time, because of the flux, there is release of calcium from the cistern, that is the reticulum, inside the cell again. So the ICF concentration of calcium increases.
So Josie, where is the sarcotubular system?
It's at the AI junction, I'll tell you. So we have a muscle fiber, we have each myofibril. Now each myofibril, I told you, has a A band and an I band. At the junction of A and I band, at here, ma. Here. This is the AI junction. So for each myofibril, at the junction of A and I, the EC, that is the sarcolemma, takes a turn and forms a tubule. And at the simultaneously, it connects with the sarcoplasmic reticulum. I will show you. This is the sarcotubular system. Present between the A and I band. So this is a basic electrical phenomenon. So in a skeletal muscle fiber, the resting membrane potential, when there is no action potential generated, is quite negative. That is minus 90 millivolt compared to a nerve fiber, which is minus 70. So, and initial excitation threshold needs to be a plus 30 to plus 40. So you have a resting membrane potential, that is, and you have a threshold. It has to reach that threshold for it to form an action potential. If the projections, if there is electrical activity, but it's not reaching the threshold, it won't form a spike potential and action potential. So you need a minimum of 30 to 40 positive millivolts. So it has to come to say 60 to 50, minus 60 to minus 50 for it to generate an action potential. So if there is an action potential, it goes up to plus 120 to 130 millivolt, and the spike lasts for around 2 to 4 milliseconds. The absolute refractory period is 1 to 3 milliseconds. That is the repolarization phase, like me. And the maximum number of impulses which can pass is 100 to 200 per second. And conduction velocity, 5 meters per second, that of the smallest myelinated nerve fiber. Not too fast, which means it's not in comparison with a nerve. So we'll come to the contractile response now to see what are the sequence of events that happen here. What is an excitation contraction coupling? So here is where electrical force is converted into mechanical force. Electrical force causes a chemical reaction. That chemical reaction forms a mechanical force. So all three takes part here. The process by which depolarization of the muscle fiber initiates contraction, which is a mechanical action, is called an excitation contraction coupling. The coupling agent is calcium. I told you how calcium is important and how it stimulates, how the concentration in ICF of calcium is required for it to form an action potential. Now, what are the sequence of events? So we'll be talking about muscle contraction, then we'll talking about role of calcium, then muscle relaxation, then the sliding filament theory in this whole contractile sequence. So on a basis, this is quite simple. We have a stimulation of motor nerve with threshold intensity. That is, the impulse, the action potential that is generated should reach above the threshold. I told you it should be 30 to 40. That is, from minus 90, it has to go to minus 50 or minus 60 to minus 40 for it to generate an action potential. That is, cross the threshold. Produces propagated action potential. Now, this releases ACH into the synaptic cleft, which binds to the nicotinic ACH receptors in the motor end plate and causing an end plate potential. Now, there is depolarization of the muscle membrane, sarcolemma, by increasing its permeability to sodium. The whole calcium, the function of calcium is not only to let calcium inside and cause depolarization, it also lets sodium inside. It opens sodium channels for sodium to enter, which aids in depolarization. Generation of action potential in the muscle fiber. Inward spread of action potential through the T system, like I told you, calcium release. and increase in concentration of calcium in the ICF by 2000 times, and hence causing muscle contraction. Now, how this calcium causes, like I told you, this calcium binds to troponin C. It moves the tropomyosin, exposes that myosin binding site. Now, actin goes and binds to the myosin, and there is ATPase activity of the myosin. That breaks the ATP in the actin, generates energy, then moves. This is basically an whole sequence of events that happen. Now, what does calcium do? It binds to the troponin C to a saturation point, causing tropomyosin to move laterally, exposing binding sites for myosin heads. Okay. So these troponin and tropomyosin, their function is to protect the actin and keep it at rest, keep the muscles at rest. That's how these TT elements work. Now, not only that, activates prosthetic group of myosin filament, which acts as an enzyme. So the calcium not only moves the actin and exposes it, but also activates the ATP enzyme I told you in myosin. ATP, the myosin head has two things, the globular heads. One is the actin binding part and then the ATPase part. So this calcium goes and activates that ATPase so that ATPase can be used to utilize the energy present in the actin. Catalyzing the breakdown of ATP to produce energy, contraction of actin-actomyosin complex, and activating the sliding filament system. Now, what happens in muscle relaxation? A few milliseconds after action potential is over, the sarcoplasmic reticulum begins to reaccumulate calcium. The calcium ions are actively pumped by the calcium magnesium ATPase into the reticulum, I told you. And then it goes into the reticulum and goes into the terminal cistern and stays there till the next action potential comes, and there is a generation of electrical difference and then the release. Once calcium concentration decreases in ICF sufficiently, chemical interaction between myosin and actin ceases and muscle relaxes. We need the calcium for it to expose. For most of the action, we need calcium. If it's not there, then the muscle activity ceases and it goes back to rest. Now, molecular basis of sliding filament therapy. Okay. In 1964, they are not related, by the way, A.F. Huxley and H.E. Huxley. They formulated this theory. So what happens is, this is the globular head of myosin I was talking to you about. So there are two globular heads per A band. So what this does is, now the whole sequence where now the myosin is bound to actin. Now what it does is the head rotates. The head rotates and it detaches. It rotates, it propulses itself a little forward, detaches. Then it attaches to the next actin. Then that rotates, propels forward, detaches, rotates, attaches, rotates, dislocates. Such actions almost 5 to 6 times it happens. And this is the mechanism with which it contracts. The contraction, I told you initially, that it moves, the I band has to move together, that the Z band length will reduce. So the length of the sarcomere will be approximately 1.5 micron at the peak of contraction. So this is how it goes: rotates, dislocates, attaches, rotates, dislocates. Around 5 to 6 times it happens, and it moves forward. So this is how. So it's here, and then rotates, goes forward, goes to the next one, again rotates, goes here. So this is another way of depicting it. So this is the active site. If this goes and attaches, this is the thick filament, this is the thin filament in a double helix structure, goes and attaches. Then the myosin head rotates, you see, it's rotating, and then it dislocates, dislodges. Then it moves forward, goes to the next actin site, rotates again. This is how it moves forward. So now that is your contractile. Now we have something called mode of contraction. We'll be talking about certain basic definitions, and then we'll move forward to what exactly happens on a day-to-day basis. We see this isometric and isotonic contraction. What happens? Now, what is the contractile component? Represents the elasticity of thick and thin filaments. Contractile, so the contractile proteins, which will be your actin, myosin, basically. Now, apart from the contractile component, we have something called an elastic component. there are two elastic components. One is parallel elastic component and series elastic component. These are basically the elasticity produced by the supporting structures of the muscle. So like for example, your parallel elastic component will be your connective tissue sheath surrounding the myofibrils. So the myofibrils will be your contractile component, which comprises 3/4 of the muscle protein, and then the connective tissue around the myofibrils will form your parallel elastic component, whereas your tendon, the elasticity of the tendon, will be formed by the series elastic component. So basically the pull and push, the tension that is created is all these three together are responsible. So the work done, the energy expenditure, all these work. Resistance to stretch is mainly due to the series elastic components and some by parallel elastic component. The myofibrils themselves act as only a passive viscous element and have very little resistance to stretch. So if a muscle is being stretched, the elements coming into play are ACC and PEC. So the 10 and a couple of so it's said, like take a rubber band. If you stretch it, the tension produced in the rubber band is equal to the amount of stretch we are creating. But that is not so in a muscle. The tension may not be directly proportional to the stretch. And this is defying Hooke's law. Hooke's law is when it is proportional. So again, a couple of definitions which tells us the length regarding the muscle state. One is you have your optimum length, the length of the muscle at which it develops maximum active tension. Resting length, the muscle length at which it is present under natural conditions in the body in a relaxed state. You need to know that many of the muscles in resting length are at optimum length. For example, your posture muscles, they are always working. They always need to be in an optimum length. That is in a state of active tension for you to stay upright. Then we have equilibrium length, the length of the relaxed muscle cut free from its bony attachment. So just the basic, the elastic component. So what is the length of that? Initial length, the length of the muscle before it contracts. So we have the muscle origin. This is the contractile component. This is the parallel elastic component. That is the connective tissue present with it. The connective tissue sheath with the component. And at the ends, at the level of insertion, we have the tendons, which are responsible for your series elastic component. So we have something called an isometric and an isotonic contraction. So first we'll be talking about the isometric contraction. In isometric contraction, so the work done, in physics, the work done is equal to force multiplied by the tension developed in that is the tension developed multiplied by the length it travels. That is the contraction that happens. So here in isometric, so what we're doing is we are keeping it stable. We are fixing the ends of the muscle. So the length does not increase or decrease. It remains stable. But there is a constant tension with varying varying stimulus. We increase the tension in the muscle. But there is no movement of the muscle fiber. So the length remains stable, but the contraction is still happening. So when the length remains stable, so the length is equal to 0. When you multiply anything with 0, the work done is 0. So work done is equal to tension into the length traveled. The length traveled will be 0. So there is no work done in an isometric contraction. There is only tension which is building up. So this is the first state. Now, and when the tension builds up sufficient enough and the force developed is sufficient enough to lift the weight, or it exceeds more than the weight, then the contractile component comes into play. Here, there is no contractile component coming into place. It is basically an elastic component. So even if there is a contraction happening and the contractile component is acting, it is neutralized by the elastic component. So the contractile component is equal to the parallel and the series elastic component. So there is no distance traveled. So it's neutralizing each other in an isometric contraction. So this happens when you're standing upright. postural muscles, this is what happens naturally. Whereas when you're running, when you're lifting something, isotonic comes into place. That is, the tension remains the same, but the length reduces. So here what happens, now there is pressure building, the force increases. At some point of time, the weight here, the force created here, it has the capacity to lift the weight. That means this has to exceed, the force generated here should be able to exceed this weight. And there is shortening of the filament. Now what comes into play when you're shortening the filament? It is your contractile component. That is your actin and myosin. So here definitely work done, energy expenditure is done. But for every muscle action, there is an initial isometric phase followed by an isotonic phase. During isometric phase, there is no work done, no energy expenditure, whereas in isotonic phase, there is, because the length shortens.
This graph.
That's simpler. There's a simpler graph, ma'am. This one. So this is with related to tension. This is the contractile component. This is the elastic component. This is the total tension. What is total tension? This is active plus passive tension. What is active tension? This is the contractile component. Tension created in the contractile component. What is passive tension? This is the elastic component. So what happens? So when you see contractile component, you keep increasing, you keep stretching it, there comes an optimal length at which it functions the maximum. So it peaks here. But if you keep stretching it, there is a mechanism which I will be talking about. It is a Golgi tendon mechanism. There is an autogenic inhibition. When you keep stretching beyond the limit, there is a protective mechanism by which the muscle involuntarily tends to relax. You can't stretch the muscle. If you go on stretching, no, it will rupture. So the optimum, this is the optimum length. That is the length at which maximum tension is generated. Beyond that, if you pull, or less than that, if the length is present, it won't contract optimally. It is not good. So beyond that, if you stretch it to approximately 3.5 micron, it will rupture. Whereas your passive component, you keep stretching it. As much as you stretch it, the tension keeps increasing. So approximately here, your total tension will be equal to active plus passive tension. When you come here, your total tension will be pretty much just your passive tension. And when you come here, the total tension will be pretty much just your active tension. You're understanding what I'm trying to say? So at the end, when the stretch at the end of the muscle stretch, like you've expanded it to an extent, at that point of time, they are directly proportional. The stretch and the elastic component. So at the end of the stretch, most of the work done is just by passive tension. The contractile component does not function there. So is what I mean. So the summation of these two are this. There's a dip. It's the same thing. So the optimal length is your 2.5 micrometer. When this is optimal, that is the I band is at the level of head zone and it's contracting well. Whereas if you keep pulling it, or if it overlaps too much, it's not too optimal. The tension created, the active tension created is not too good. Now, coming to something called a load velocity relationship. This is with respect to isotonic. So they have done an experiment where they wanted to check the isotonicity. So they have disconnected a muscle. They fixed one end, and they have attached weight to the other end. Now they keep stimulating the muscle. Now the level at which the muscle contraction, the force generated in the muscle exceeds the weight, it pushes. But there is a velocity at which this happens. What they are trying to say is the weight attached is your afterload. If you increase the weight, if you go on increasing the weight, it's obvious that the velocity at which it contracts will be less. This is like pretty much basic common sense. That's what. So as you increase the weight at the end of the muscle, the velocity at which the contractile component acts is slow. Now let's come to the properties of a motor unit. Definition: motor neuron. What is a motor neuron? Each ventral horn cell along with its motor nerve is your motor neuron. Motor unit: each single motor neuron and all the muscle fiber it supplies. Basically, the efferent system. So the properties: the number of muscle fibers in a motor unit varies inversely with the precision of movements by the part. So assume you're writing the amount of motor units. So the number of motor units is one nerve supplying the number of muscle fibers. It should be less when you're writing because you need more precision. Correct. So multiple motor units need to be in place or active when you're writing. But when you're like walking or something, each motor unit can supply a large pack of muscle fibers. That's okay because you don't need much precision to walk. But for small, finer motor activity, the amount of motor fibrils supplied by the motor nerve should always be less. That's what they mean. All the